of the each mass, just finding the kinetic energy and the potential energy of the system, we are able to obtain the equation of motion. Fine. That is very important. Okay. So now the thing is that so let me just repeat again. So what we have done so far is the m x double dot plus c into x dot plus k into x equals to some forcing function, right? That is pt, time dependent force. And we have gone through the eigenvalue problem. So eigenvalue problem is k into that u is equals to omega square m into u, right? That is my eigenvalue problem. So if I solve this, I will get eigenvalues and eigenvectors. Okay. So these eigenvectors are nothing but your mode shape. Okay. Normal mode or mode shapes. And if I take the square root of this, so I will finally get omega 1, omega 2. These are my natural frequencies, and I will arrange omega 1 less than omega 2 less than omega 3 like that. Okay, from the lowest to the highest. Okay, and omega 1 I am calling as the fundamental frequency. Okay. Then we have proved the orthogonality relationship, right? Okay, so that we have many times we have done, and using the orthogonality relationship and assuming the solution, this solution that xt, that is xt as a superposition of the modes, that is the modal matrix. What is modal matrix? The u is nothing but first mode, second mode, and so on and so forth to the nth mode. Okay, right? So modal matrix into the generalized coordinate eta t. Eta t is the generalized coordinate. So if it is n cross 1, then it is n cross n into n plus 1. Okay, so this is called the modal coordinate or principal coordinate, and this is my actual physical coordinate, and this is the modal matrix. So if I substitute this solution in this equation and then pre-multiplying by u transpose will result in u transpose m into u. This already we have done. I'm just once again repeating it, okay, so that you can recollect it or remember it. Okay, so just substituting this equation here, I mean this assumed solution here, okay, and pre-multiplying the equation by the u transpose. Okay, eta t equals to u transpose into pt, right? Correct. Now this we have defined as the modal mass matrix, modal damping matrix, and the modal stiffness matrix. So what is that modal mass matrix? M tilde is equals to u transpose m into u. If your eigenvectors are mass normalized, then it is nothing but an identity matrix. Right? If it is mass normalized using the orthogonality condition, and if this is mass normalized, then it is nothing but an identity matrix. So that is basically one diagonally one. Okay. If you do not mass normalize, diagonally you will get some values. Okay, that we call it the MR, that M1, M2, M3 like that. Okay. Then C tilde is the U transpose C into U is the modal damping matrix. So this is the modal. So these are all available in your PPT that I have sent. This is called the modal damping matrix. Okay, and we have seen that if C, for some special value of C, we have not discussed that so far. What is that C that will make it diagonal? Okay, so we call this matrix as classical damping matrix. Classical damping matrix. If you have any issue, you should ask me. Okay, if you have any issue in understanding anything. So if this is a classical damping matrix, in this case it can be diagonalized, and the diagonal will be nothing but 2 omega r, I mean 2 omega 1 zeta 1, 2 omega 2 zeta 2, like that, 2 omega n zeta n. Okay, right. And then K tilde is the modal stiffness matrix, that is U transpose C into U. Again, if your U is mass normalized, then U transpose K into U, then it will be nothing but the spectral matrix. Right? Okay, that is basically the diagonally omega 1 square, omega 2 square, so on and so forth, omega n. This we have already discussed, and you can see. So basically, what is happening? So this equation is getting diagonalized. Okay, so instead of n, so this is all n by n, right? So n coupled ordinary differential equation, we are going to solve single equations at a time. So that means for, let's say, arith mode. Okay, arith mode, we are solving basically eta r double dot, right? Plus 2 zeta r omega r eta r dot t, this is t again, okay, plus omega r square eta rt is equals to some pr star t or something. So this type of equation I will get where r varying from 1 to so on and so forth n. Okay. So I know this. What is the solution of this? Right. This is a single degree equation of motion of a single degree of freedom system subject to this forcing function. If this forcing function is not there, then it is the p vibration problem. We know how to find out eta rt. Okay. And I already discussed how to find out the initial conditions in the modal coordinate, because your initial condition will be given in the physical coordinate, right, in xt. So you have to, from here you have to find out the initial conditions in the, that is initial displacement at time t equal to 0 and initial velocity at time t equal to 0. From this expression you have to find out in the modal coordinate or the principal coordinate, okay, by invoking the orthogonality principle. Already discussed many times. Okay, so once you got that, you can solve this equation. Okay, so then you will find out the expression for the eta rt. Okay, and this eta rt finally you have to substitute here, because our aim is to find out the response of the system, which is xt, not the eta t, right? Okay, xt is the physical response. So u is known to us, that is the modal matrix is known to us. Now we will substitute the eta t here, vector here. Okay, eta t vector how will you find out? Because here eta t is nothing but your eta 1t, eta 2t, like that, right? Eta nt, something like that. So for each one you will find out from solving this equation, and finally this you will substitute in this expression to get the result in the physical coordinate. Okay, that we have discussed many times. Okay, right. And then we discussed how to find out the equation of motion, formulation of equation of motion using Lagrange approaches. Okay, because we starting at the starting also we talk about that, but we are mainly concentrated on the Newton's law or the D'Alembert's principle by drawing the free body diagrams of the each masses. Okay, and then writing the equilibrium equation. Okay, here that is not required. In the Lagrange approach you have to find out the kinetic and the potential energy of the whole system. Okay, then you have to apply the Lagrange equation, which is coming from Hamilton's principle. Okay, right. Now, so while I am solving this equation, let us see. Okay, so again let me write m x double dot t plus c x dot t plus k into xt is equals to some pt, right? So what I told that xt, I am assuming my solution, which is n cross 1 equals to modal matrix u into eta t, right? That is what I told. This is nothing but in extended form. I can write that is u1 eta 1t plus u2 eta 2t plus so on so forth un eta nt. Right? That is what it is. That is in the matrix proper form I am writing here, because u is nothing but u1, u2 side by side, right? That is all the mode shapes. Okay, and this is written in the vector form, that is eta t. Correct? Okay. So now let's say in a system the aim is 10,000. Okay, so there is a 10,000 mode. Okay, that means your mass matrix, stiffness matrix, damping matrix, and stiffness matrices are all 10,000 by 10,000. So let us say that we do not want to use all the modes in our analysis. Okay, and as I already mentioned, maybe at max 100 modes are good enough for complicated, even for complicated system. For normal system, it is a 10 to 20 mode is more than enough to get a engineering solution. Okay. Okay. So let us say I want to truncate somewhere here. Let's say I want to use some first 2 modes or 10 modes. Okay. So let us say the number of mode I want to use the n hat, which is less than n. So this shows the number of mode I want to use. Number of modes to be used in my mode analysis, which is much less than n. Let's say it is 100. I want to use the 100 mode. So then my this thing, okay, n plus 1 will be, so what I will use? Instead of all the modes, u2 till u n hat into eta 1 t, eta 2t, so on and so forth, eta n hat t. Okay, right? So or I can write it like this: u hat into eta hat. This is n cross 1. This is n cross n hat cross 1. Any issue with this expression? Or the dimension of the matrices, or what it is, how it is different from this? Any issue? You have to reply. Okay, you have to reply. Don't be silent if you do not understand. Okay, maybe 90% people are understanding, 10% people those who are still silent without understanding. So I repeatedly request them, please do not hesitate to ask me. Okay. Okay, very good. So basically what we are doing, instead of all n modes, I want to use truncate it. Okay, that is the truncated it to n hat. Well, n hat is much less than n. Okay. So in that case, my xt is now u hat into n hat. Okay. So if I substitute now this in my equation of motion, okay, then what will happen? So my so equation will be like this, right? Modal mass matrix into eta hat t double dot plus modal damping into eta hat dot t plus nodal stiffness into eta hat t is equal to some forcing p hat or okay p star. So now tell me what is the size of this or this or this. Quickly tell me. You have understood everything, so please quickly tell me what is the size of this.
N cross n. N cross n.
N cross. How it is coming m hat? Okay. Image is no, I'm considering I mean asking in this context, right? That truncated constant condition, that is when I am using n hat mode instead of n. Okay. What is the size of this m, c, and k?
So n into n hat.
Okay. Okay. So first of all, you should understand that the whatever transformation, anything you do, your mass matrix, stiffness matrix, and the damping matrix should be a square matrix. Okay. Very, very unspecial case. Those are, I mean, we are not beyond our scope, even beyond MTech also. Okay. So it is always to be a square matrix, first of all. Okay. So there is no chance of n hat into n or n into n hat. Forget about those things. Okay. Okay. What is m hat? M hat equals to u hat transpose m into u. All agree with me? What is U hat transpose, dimension of U hat transpose?
One cross n hat. One cross n hat.
No, n hat cross n, right?
Oh, yeah.
This is n cross n hat. So finally this has to be n hat cross n hat. That is, so initial my mass matrix was 10,000 by 10,000. Okay. Now it is 100. If I use 100 mode, it will be 100 by 100. So that means instead of solving this n equation, so first of all it was the coupled equation, okay. So if I want to use only 100 modes or 10 modes, so my system dimension is getting reduced. Even let's say the damping matrix is such that we are not able to uncouple it, okay. We are not able to solve it single equation. Let's say this is not a classical damping matrix, okay. I mean, let's say this is not a classical damping matrix. So in that case, your C hat will not be a diagonal matrix. That means you will not be able to see the single equation, single degree of freedom equation. But still, you see the dimension of the size of the system. This becomes reduced due to this modal transformation, that is this. But obviously using truncated mode. Okay. So please listen carefully my each and every word. And if you do not understand, please reply me back. Okay. Right. So
Sir.
yes.
So like on what basis we are truncating the values? Like will it not affect the total result? Like we are truncating 10,000 to 100 and all nodes.
Correct. So that is the what I want to just going to tell you. Okay. Now there is a basis, right, to how many modes to include. But as I already mentioned, for the structural vibration, the initial few modes are highly important. Okay. And actually there is a terminology called the modal contribution factor. How much the modes they contribute. And I already told you, I think you can check it. Okay. Just take a 4 degree or 5 degree of freedom system, but although it will be difficult for you to solve, but maybe let's say 3 degrees of freedom system. Okay. And then you see how much your first mode is getting contributed to the response. Okay. Or the just considering the first two mode, forget about the third mode. Okay. Then you will able to see that the first few modes are really very important. Okay. Right. What is the reason is that, okay, you see, because if I go deep into the detail, let's say this is a cantilever tower. Okay. So what is the first mode? The first mode of vibration will be like this, right? First mode of vibration. The second mode of vibration will be something like this. Okay. There will be one cross. Similarly, third mode of vibration will be like this. Okay, I think I have shown one picture or something like that. There will be something.
Yes, sir.
Okay. So similarly, you see What will be the mode step of the 100 mode or the 2000 mode or whatever? So it will be complicated. I mean, there will be a lot of nodes coming into the picture. Right? So what do you feel is the easiest way to vibrate? This or this?
First one.
First one. Okay. You see, humans are also lazy. We are also lazy. We do not want to much study and get a complete the process, right? Right. So similarly, structure is also very lazy. Okay. Structure do not want to like this. Too much energy required to vibrate like this or in the harmony. He said that let's vibrate like this. Okay. So initial few modes which are easy to vibrate or there is less energy required to vibrate that mode. Those are got mainly excited. Those modes are got mainly excited. Okay. Obviously the other modes also excited, but their contribution is very less. Okay. And we'll be able to see that when I discuss about the continuous system. Continuous system, number of degrees of freedom infinite. Each and every point there is a degrees of freedom, so infinite degrees of freedom. Okay, but for this kind of cantilever beam or cantilever tower, we will say the first 5 or 4 more. Exactly, I do not remember, but I think 4 or 5 more. It contributes 80% to the total response, or more than I think 80% of the total response. Let's say your actual response is 100. I mean, at some point, I mean the peak response is 100. So we'll get 80% of the response by considering only the first 4 modes for a cantilever system. Something understood, right?
Yes, sir.
Yes.
Got it.
So even there can be a quantification that's called modal participation factor. How much a mode is participating? Okay, but that detail we are not going here. Okay. Understood? So yeah. So but one of the most important thing here I want to discuss is that. So I am talking about here I want to consider 100 mode. So that 100 mode doesn't have to be the first 100, right? I can very well choose whatever. I mean the first, second, 50th, 150th, 250th, like that I can choose 100. Okay. Because I have the flexibility, right? I can choose here. Okay, if you do not understood, let me repeat. So what I am trying to say is that xt is equals to your u1t. I can say no, second mode I will not consider. Fifth mode I will consider. I will consider no, 10th mode. Let's say I am to consider 3 mode only. Then this will be your eta 1t, eta 5t, eta 10t. Okay. So now in this case, what will be the dimension of the m hat for this case? I mean, how many equation size of the what is the equation? If it is not uncoupled, how many coupled equation I have to solve through this modal transformation?
3.
3 by 3. Yes, 3 by 3. This is m hat will be 3 by 3, and that is similarly for c hat and similarly for here. So even if my C matrix is this matrix is non-diagonal, that means the damping matrix is non-classical. Still, you are solving a very few number of equations, and you are you are able to obtain a reasonably accurate answer which can be used for engineering purposes. Right? Okay. Okay. So now, so we have seen the orthogonality, right? So orthogonality relationship is that U R transpose M into US is equals to 0 and 1, that is we are in terms of Kronecker delta, I can write delta RS. So if R equals to S there is 1, and if R not equal to S there is 0. And then UR transpose K into US is equals to omega R square delta RS, right? So these are the orthogonality relationship. So there is a family of orthogonality relationship, but that is not in your scope. Just for sake of information, remember that this is the family of orthogonality relationship. Okay. So just see carefully. US transpose M bracket start M inverse K power to the power B U are equal to 0. Okay. So you can try to prove this starting from the eigenvalue problem. So first try by yourself, that is K into U R, let's say Rth mode or set mode, whatever. It will satisfy all the modes. Omega square M into U. So this is your eigenvalue problem, right? And then you have the two orthogonality condition, right? Using this and this, try to prove this. Okay? So that you can try by yourself, or if you fail, then you please refer to the book of Chopra or Klaffen-Penjan is also there. Okay. But that is not in your part of the syllabus. But just for sake of information, I am trying to say that there is a family of orthogonality relationship available, not these two sets. So these are some special set. You see, if I put b equal to 0 in this equation, we'll get this one. If I put b equals to 1, I'll get this one. So there are the two basic orthogonality relations, actually, which is good enough for our present purposes. But there exists a family of orthogonality relationship which can be written in a compact form like this. Okay, and we can recover actually these two basic relationships by putting p equal to 0 and b equal to 1. Okay, so that if you are interested, you please see it by yourself. Okay, so now. So I've spent a lot of time regarding this. These are all simple things that you understood, right? So last time I'll ask you that I hope everybody of you have understood the orthogonality relationship, eigenvalue problem, and the mode superposition method. Okay, because if you don't understood that is, there is, again, no point of going ahead to the continuous system, or that from this course dynamic system you have not learned anything if you do not understand that thing. Obviously, for that you need to know the single degree freedom system also, because finally we are solving this single degree freedom system and getting the responses. Okay. So if you have any doubt related to that or this thing, then you can ask me anytime. Okay. Fine. So this I have discussed. What is that? Okay. You can read it. Now comes to the remaining thing, that is balanced structure, is the construction of the damping matrix. Okay. Damping is very complicated phenomenon. You see, in the stiffness, right, if the system properties are given, the cross section, dimension, all those things are given. Let's say a rod or a beam is given to you. Its E is given, Young's modulus is given, cross section, the moment of inertia I is given, right, length is given, cross section area A is given. So if those type of parameters are given, then from that you can very easily find out, or the standard procedures are there, approaches are there, okay, to find out the stiffness coefficient or finally the stiffness matrix, correct? But damping you cannot find out like that, okay? Or even if it is, everything is available to you also, if you try to find out the damping matrix or try to construct the damping matrix in that manner, we will lose some information. What is damping? Damping, what is doing? It is the energy dissipation, right? So that's why damping is usually not constructed in that manner, like from the dimension of the structure, all those things. It is the energy dissipation mechanism. So usually we express the damping matrix in terms of the modal damping ratio. What is modal damping ratio? That is zr. We talked about, right? That is, we are calling that if it is diagonal. Yeah, so U transpose Cu. Okay, so here C is the modal damping matrix and it is diagonal. So usually we express the damping matrix in terms of the modal damping ratio, that is zeta1, zeta2, zeta n. So zeta1 is the first mode modal damping ratio, second mode modal damping ratio, nth mode modal damping ratio, right? Okay. So when we need this matrix, okay. So if I know zeta1, zeta2, zeta3, okay, and if I can construct the damping matrix like this, we do not need this, right? C matrix we do not actually require. Okay, we just write the diagonal, modal matrix like this diagonally. So when it is required, so when this C matrix is non-classical, then it is not be diagonal. This transformation will not be diagonal. Okay, so when this is non-classical matrix, okay. So linear system with non-classical damping or analysis of non-linear system. Why for non-linear system you cannot do this? You cannot do the U transpose. You cannot find out the modal damping ratio in that form. Any idea? Just give some idea. Tell me. Let it be wrong, no problem. You just think about the very simple question. Okay. Why for a nonlinear system that that modal transformation I cannot do and make it a diagonal matrix and just use the modal damping ratio, then write 2 omega 1 zeta 1. Why I cannot do that? What prevents me? I need the expression for C. I cannot do the C tilde, that is modal damping matrix. Any idea? Just whatever coming in your mind. Tell me.
Sir, in all the equation which we read, we actually assumed it to be a linear system.
Yeah, so what basic things we cannot apply there? You see, okay. So for linear system, the modal analysis or mode superposition, that term, right? Just keep in your mind. So that is only valid for if the system is linear, right? So what we are basically doing, we are solving in from n simultaneous equation, we are uncoupling it, right? During that uncoupling, so first of all, we are assuming that the my xt is equals to u1 eta 1 plus u2 eta 2 plus u3. That is one superposition of the response from all the modes. And then also, when I am transforming, right? So the transformation that we are doing the superposition actually, right? So that superposition principle is not valid for nonlinear system. Superposition is only valid for the linear system. So that's why for the analysis of the nonlinear system, there is no other option, but you have to solve the differential equation directly, okay, by constructing the C matrix, okay. And if the linear system, if the system is linear but it is a non-classical damping, that means you are not able to diagonalize it. So the transformation, that is U transpose C into U. Okay. Then also you need the damping matrix. Okay. Otherwise, if it is a classical matrix and you know that we'll be able to diagonalize it, then our damping ratio, that is if I know zeta 1, zeta 2, 3, then I can just construct the modal damping matrices 2 zeta 1 omega 1, so on and so forth, 2 zeta n omega. Just diagonally I will put it and finish. So whatever I just told, it is written here, the Y damping matrix, we should not construct, or it is not a practical procedure to construct the damping matrix like we do for the stiffness matrix or stiffness coefficient. Okay. Just read it, this part, understand. And also read this one. So damping is generally specified by numerical values of the modal damping ratio, that is zeta 1, zeta 2, zeta 3, zeta like that. And these are sufficient for analysis of linear system with classical damping. We'll concentrate only on this, okay, for this class. We'll only consider the linear system with classical damping that can be diagonalized, okay. And I will just briefly give you the idea. If it is not classical damping, that means you will not be able to diagonalize, okay. Then what are the procedure to handle it, okay. One thing you understood, you just solve the differential equation directly without the transformation. That is obvious. So that will just briefly touch upon that. But our main target is to discuss about the formulation of the classical damping. Okay. So if you have finished the reading, so please read this also. Even if these properties are known, the resulting damping matrix would not account for significant part of energy dissipation by infliction, like for civil engineering structure, the steel connections, opening and closing of microcracks in concrete, stressing of non-structural elements, and there are so many things. These are just named to few, and it is still not known what mechanism is actually going on in that energy dissipation. Okay, so you cannot capture all those things individually, miss something. So it is better to just do the experiment, find out the modal damping ratio, and do the modal analysis. If you are sure that your damping matrix is, your damping matrix is classical, then you can just use the modal damping ratio to construct the modal damping matrix and solve the ensuing equation. Okay, right? So that's why it is written here. Okay.
Sir.
Yes.
So in the first point, it says that damping matrix do not contribute for the significant energy mechanisms in the structure.
Where it is written damping matrix?
Next page.
Yes,
in the first point that the resulting damping matrix would not account for a significant part. And in the next point, it says that
where it is written damping matrix?
Yes, the resulting damping matrix would not account for a significant part.
No, you have to continuously read it. It is associated with this para also. What it is saying? It is saying that it is impractical to determine the damping matrix. We are talking about this damping matrix in a manner similar to structural stiffness matrix. Okay, actually you don't know what is structural stiffness matrix right now, but anyway, So the structural stiffness matrix is like for beam, right? You might have heard about this thing, right? 12 EI by L cube, 6 EI by L square, like those things, right?
Yes, sir.
That means, so this modulus of elasticity, if you know Li, if you know L, and for axial stiffness it's called EI by L, EA by L. So if you know this EA, so you can very easily construct your stiffness matrix, right? And that is well established. That is absolutely perfect. Okay. From the basic mechanics angle. But the similar approach you cannot apply to construct the damping matrix. That is what you're trying to say. And even if you do that, let's say everything is given to you, all information, and you have obtained the damping matrix in that manner, the manner in which you obtain the stiffness matrix still will miss something. That is what they are saying. The significant part of the energy, so something will miss, that due to the energy dissipation that is not clear to us, or some of which are even hard to identify. Clear?
So then this next line, the damping matrix for a structure should determine modal damping ratio.
Total damping
Uh,
ratio.
this corresponds to stiffness matrix, structure stiffness matrix. Or
Modal damping ratio stiffness matrix. Where it is written?
no. So like you are saying, it's hard to determine the exact damping ratio matrix.
No, you get confused. Okay. I'm saying that the way you are constructing the stiffness matrix, right? Okay.
Yes, sir.
So that procedure you should not apply for the construction of the damping matrix. Okay. That is this line. It is impractical to determine the damping matrix in a manner similar to the structural stiffness matrix, right?
Okay. Okay.
That is okay. So that's why they are saying that if you, let's say you obtained in a manner the way stiffness matrix is obtained, you construct the damping matrix. So then you will, it is saying that you will miss something, right? That is the energy dissipation mechanism you will miss. Okay, right? If you want to obtain in an analytical manner, right? Like the way you do it for the structural stiffness matrix, correct?
Okay, sir. Got
This
it.
part is clear?
Yes, yes.
Then it is saying that you should do from the modal damping ratio, that is zeta r, zeta 1, zeta 2, zeta 3. From the experiment you find out the modal damping ratio. That you know, right? Already you want to find out. You can find out from the either half power bandwidth or like logarithmic decrement for each by exciting each mode individually. Okay, right?
Yes, sir. Got it now.
Got it. So now, so that means if so C tilde is equals to what? Let me just write it here, is C into U, right? So I want to construct this matrix, and if it is a classical damping matrix, we are talking about classical only. So then what is my this matrix is 2 zeta 1 omega 1, 2 zeta 2 omega 2, so on and so forth, 2 zeta n omega n. For rth kit 2 zeta r omega r, like that, diagonally, right? Correct? That is U transpose C into U. So please listen carefully what I am now just going to demonstrate, or just talking about the classic construction of classical damping matrix. Okay, because I will ask, there will be one question in any one of the exam related to this classical damping matrix. Okay, this is clear. There is no issue with this, right? If C is classical.
Yes, sir. Clear.
Whereas omega 1, omega 2 is, you already know, zeta 1, zeta 2, zeta 3, all these things are the modal damping ratio. First mode modal damping ratio, second mode modal damping ratio, like that. Okay. In general, it is the, let's say zeta r is the rth mode modal damping ratio, r equal to 1 to n. Okay. Now, so what comes in your first mind? What should be the structure of C such that U transpose CU become diagonal? Forget about this part. I'm just asking, what should be the structure of C? What could be the structure of, not should be, what could be the structure of C so that U transpose C becomes diagonal? What first thing come in your mind? What should be the form of C? Or which thing you can utilize to construct this C matrix so that when I do the transformation U transpose C, it becomes diagonal? What thing comes in your mind? Using the whatever idea we have acquired so far. I'm again repeating, using the idea whatever acquired so far of the orthogonality. Basically, why it is diagonal? Why this is getting diagonal? Because of the the orthogonality condition, right? So what could be the pattern of C or type of C so that this transformation become diagonal? What first thing comes in your mind? Anybody? Okay, let me give some hints. Just think about the orthogonality relationship. So what should be the form of C? What pattern of okay. Now tell me, this is diagonal, or if I do the transformation, it is diagonal or non-diagonal?
Diagonal.
So now if I use the C as some constant A naught into M, if I put it here, then this will be diagonal or non-diagonal?
Diagonal.
So the first thing that comes on our mind is either mass proportional or stiffness proportional damping. That is the idea. So let us first call it about the mass proportional damping matrix. Okay, so that means in this case my C will be nothing but some constant, just A naught I am calling it, A naught into A. Correct? So now tell me, because what I told that C tilde is the modal damping matrix, that is U transpose M into U. Correct? Okay. So now can you tell me, now I will ask you to do, what is the value of zeta? Tell me.
So shouldn't it be A naught M?
A naught?
Like U transpose A naught M U.
What you are saying? You are giving the value
C
of
cap,
zeta.
sir. No, sir, I'm telling about that C hat.
Yes. This too we know already, right? Right?
Yes, sir. So that should be A naught M.
Oh, sorry, this is C. Sorry, I mistake. This is C. Yeah. Yeah, you tell me now what is zeta? Yeah, it's C, correct. It should be C. That is what you're trying to say, right?
Yes, sir. I thought to say like since you substitute C naught as A naught M, so if you are writing M, then it will be M.
I'm trying to write the general expression. Okay.
Okay.
Now tell me, yeah, then you substitute it, whatever you do, then tell me what is zeta. For arith mode, basically. Come on, please do. Everyone, what is zeta?
So U1 transpose M U1 by 2 omega R, or UR transpose M UR by 2 omega R.
Then invoke orthogonality condition. Now you have already learned all those things. Now don't tell me like that. You invoke orthogonality condition. 10, 20 times you have discussed it. Yeah, anybody else, please, come on. Very simple. What is zeta? You see, the same thing is going on again and again in a repeated manner, but you are still not able to do it. That is the beauty of it. So that's why you have to try to write this equation by your own, okay, and practice it. Okay. That is the idea.
So it's the matrix or normal is right, like you.
Obviously, we are
Okay, then it will be 1 by 2 omega R.
1 by
2 omega R.
A naught Venice.
No, sir, then it will be A naught by 2 omega R.
A naught by 2 omega. Who are not agree with this expression or not able to find out this, please respond. Otherwise, I'll just move ahead. So everybody getting this? This is correct. Please reply. I am repeatedly asking you. Okay. If you are not able to understand, that is very not a good thing. Okay. So just tell me whether you understood or not, so that now you clear your doubt. Okay.
Yes, sir. Getting same A naught by 2 omega r.
Fine. Any other people? Anybody else not able to get it? Okay. Fine. So our aim is to construct the damping matrix, right? And in this case, we are talking about mass proportional damping. I have to construct this. So in that case, I have to find out A naught. M is known to us. If I know A naught, then I'll put it A naught here. I'll construct the damping matrix. Finish. Okay. So for that, what I have to do to construct A naught? So I have to know the damping matrix. Damping ratio of a particular mode. So let's say I have given you the damping ratio of the first mode. Omega 1 for first mode. I have given you zeta. So what we will do? We will substitute this one here. Listen carefully. So omega 1, you know the omega 1 and corresponding damping ratio I have given. I have done experiment and I have tell you it is the 5%. So you will put it here. You will be able to obtain A naught. Put it here. Construct the damping matrix. Done. Okay. Now if I ask you to do or ask you to find out what is the modal damping ratio for the 15th mode. How will you find out? First of all, you will be able to find out or not? I have given only one information. I have given the modal damping ratio of the first mode. Okay, that is it. Only this one I have given you. Only one information I have given you. Then I am asking you to find out what is the modal damping ratio for the 15th mode. Will you be able to find out or not? If no, then why not? And if yes, then how? How will you find it? Come on, reply.
So yes, sir, we can find.
How will you find out?
Like since C equal to A naught M, so the 15th diagonal element, like we can equate it like 2 omega r zeta 15 will be that value, or else from this, if you know omega 15, we can find.
Yeah, that is right. You can directly find out from this expression, right? Why going there? Correct? It is R. So zeta 15 is equal to A naught by 2 into 1 minus omega 15. This is known to you, the natural frequency of the system. This we have calculated from this information. You can calculate any zeta 15. So you can 15, zeta 20, zeta 30, whatever, just by changing the frequency, right? Is it clear to you? Is it clear to you?
Yes, sir.
Okay, so what we can do, if I know the modal damping ratio of the one mode, then I can find out the modal damping ratio of any other mode, and we can construct the damping matrix in this case. That is called the mass proportional damping. Okay, and obviously you can see here. So here the damping ratio is proportional to the 1 by omega r. Okay, so as the frequency increases, the damping ratio will what?
Increases.
Increases. As frequency increases, damping ratio increases.
Sir, yes. Like omega will, oh, sorry, it will decrease. It will
Come
decrease.
on, what is inversely proportional?
Yes, sir.
What you are, okay, so it will be like this. Natural frequency zeta r, it will be something like that. Got it? Okay. But again, these actually not represent the actual scenario, an actual physical system. In actual physical system, at least few modes, let's say mode number 5 to 10, they're more or less same. The damping ratio, modal damping ratio are little bit different, but not like that. It is continuously decreasing. Okay. So we cannot use this model, that is mass proportional, only the mass proportional damping matrix for our real structural system. So now comes to the second thing that are come in mind is the what proportional? Stiffness proportional, right? Because that will also make the system diagonal. Now, stiffness proportional damping matrix. Okay, so in this case, C equals to my A1, let's say, into K. Correct? Okay. Again, my C tilde is U transpose C into U. Now quickly tell me what is zeta R?
A naught omega by 2.
Huh?
A naught
A naught
omega
omega
r by
A1 omega by 2.
A1
Omega r by 2.
r by 2.
omega R by 2. Correct? That is what, right?
Yes, sir.
Anybody has any doubt with this zeta R? Anybody has any doubt? Maybe I am too many time asking. Okay, no problem. So again the same thing. So if I if I give, you see, this is for example, right? What I am writing is omega 1 zeta 1. So I can give for any mode, right? I can give the information of the modal damping ratio for any mode. From that you can find out A0. So this is just for example. I should write here for example. Okay. So I will give you modal damping ratio for any mode. Then you will find out A0 and construct the damping matrix. And for any other mode, I have written here 15. That doesn't mean you can only find out 15. You can find out any other modes. Okay. Similarly here, I will give the information of damping ratio of any one of the mode. Just one mode I will give. You will find out A1. Put it here. Construct the damping matrix. And find, if I ask you to find out any other mode damping ratio, similar manner you can find out. Clear? Okay. So now here, zeta R is proportional to omega R linearly. So in this case, it will be like this. Okay. Again, that is also not real practical structure source. Experimental evidence is not satisfied. Okay. So then comes here comes the more realistic estimation, or also not estimation, realistic formulation of the damping matrix, which is nothing but the mass and stiffness proportional damping matrix. Proportional. And these matrices are quite frequently used for our structural dynamics purposes. Okay, without thinking too much, we will just use this mass and stiffness proportional damping, quite popularly used for most of the structural system analysis. So in this case, C is nothing but your, just add that two part, A0 M plus A1. So this is called the mass and stiffness proportional damping matrix, or popularly known as the name of the inventor, Rayleigh damping. It's called the Rayleigh damping by the Lord Rayleigh. Okay. Okay. Now quickly tell me what is zeta R?
So A naught by 2 omega r
A0 by 2 omega R.
plus A1 into omega r by 2.
Correct. Anybody has doubt with this? Anybody? And this actually represents our physics, more or less accurately the physical experiment that we have conducted actually. That is have been done. So you can, what is that one? Yeah. Let me just copy this figure. I do not want to plot it. You can see it, right? So that is your Rayleigh damping. This one is your what proportional? Mass proportional, right? Mass proportional. That is, let me write just like that. So it is C equals to N0 M. This one C equals to A1K, right? So in this case, zeta, here it is N is written, okay, N is written. N R doesn't matter, is equals to N0 by 2 omega N. And in this case, zeta N is equals to A1 omega N by 2. Okay? So first one is like this, second one is like this, the Rayleigh is like this. You see, at least for this range, right? This range, Rayleigh damping is, you see, it's not much of difference. It is not like that it's continuously decreasing, or like for stiffness proportion continuously increasing. At least for some range of frequency which is maybe of the practical interest, right? Rayleigh damping is providing the reasonable result. Okay. Not much of difference in the damping ratio between this this frequency, right? This is frequency omega n zeta I. Okay. So for more, as I already mentioned, this Rayleigh damping are quite commonly or frequently used for the structural dynamics purposes. Okay. So please remember that. So now you tell me. Just stop it here in 2 minutes. So here in the mass proportional, if I give damping ratio of one of the mode, one of the frequency, then you can find out A naught, and you can find out the damping ratio for any other mode, right? Similarly for stiffness proportional, I'll give you the damping ratio for one of the mode, then you can find out the damping ratio for any other mode. But is it possible for this if I give the damping ratio for only one mode? Is it possible?
No, sir.
No. Why?
Because it's like A naught and A1 are one.
Yeah, because there are two unknowns. You have to give two conditions. You have to give, right? So here the unknowns are A naught and A1. So I have to give at least information of the two mode. Okay. So let's say zeta I corresponding to mode omega I and zeta j corresponding to mode omega j. Got it? So if I give the information, then if I give you the information, then you will get two equations in two unknown. Solve it and tell me quickly what is A naught and A1. Expression for A naught and A1. So zeta r is equals to A naught by 2 into 1 by omega r plus, what is that? A1 by 2 into omega r. R can be anything. So I have given you the two information that for omega I it is zeta I and omega j it is the zeta. So for two mode I have given you the modal damping ratio. Substitute there, you will get two equations. Solve it to get A naught and A1. Tell me what is A naught and A1. Anybody did not understand what I am asking you to do? Please reply. So since here two constants are there, A naught and A1, so I have to give the information for the two modes, right? So I am giving here for ith mode and the jth mode. Ith mode modal damping ratio zeta I and jth mode modal damping ratio zeta z. So that I can find out A naught and A1. Once I obtain A naught and A1, okay, then I will put it here. A means M and K is known to me. I can construct the Rayleigh damping matrix, okay, or mass and stiffness proportional damping. And once I know the A naught A1 from this expression, I can find out the, for any mode, I can find out the damping ratio. Okay? Like we do for the mass proportional damping and stiffness proportional damping earlier. What is A naught A1? Come on.
So I got A1 as 2 into omega I zeta I minus omega j zeta j by omega I square minus omega j square.
Can you please tell me again?
A1.
A1.
Yes, sir. I found A1 as 2 into omega I
Yes.
zeta I
2 into omega into zeta I
minus 2 into omega j zeta j.
Omega I into zeta j.
No, sorry, omega j zeta j.
Omega j zeta j.
By omega I square minus omega j square.
By omega I square minus omega. That is what, right?
Yes, sir.
And A naught equals to 2 into
2 into
eta I divided by omega I
eta I by omega I
minus eta j.
minus eta j.
So this whole in bracket from eta I divided by 1 by omega I square.
1 by.
Yes.
Okay, then you can put omega I square top, right?
No, sir, it's term 1 by omega I square minus 1 by omega j.
1 by omega square minus 1 by omega j.
Yes.
So I am not verifying this thing because this is too trivial to verify. Okay, two equation, two unknown, simple, solve it and find out n or a1. You can, for convenience, you can write it in the matrix form also. Okay, very simple, right? Two equation you write and then invert it basically, right? So then you will get something into zeta I, zeta. So basically this something need to be filled. Okay. Okay, so I hope everybody understood it. Okay, so I'll stop it here, but I'll still may remain here for 2 minutes. Those who are still hesitant to ask me, I'm giving them the opportunity to ask me for the last 2 minutes. So please ask me if you have any doubt. Otherwise, those who have understood, they can leave. The class is formally over. So we'll continue with this thing in the next classes again. So we'll see one example also we'll see. Okay, and then we'll just briefly talk about the extended Rayleigh damping, but obviously we're not going to discuss much about that. That will be too much for you. Okay.
Sir.
Yes.
So like you shown the graphs of delta.
Correct.
Damping ratio and natural frequency.
This one?
Yes, sir.
Yes.
So if we see this graph, the damping ratio corresponding to omega I and omega j should be same.
Same? Who said omega and omega is same?
No, so like in the graph you have drawn these lines, na?
Oh, that is actually what you are saying this two vertical line, right? Okay.
Yes, sir.
That is, yeah, you are right. I mean, I am going to use that is coming to the next. That here I told omega is zeta I, omega is zeta j, right? So the expression is further simplified if you consider that for both the mode, the damping ratio is similar. And usually we try to choose because you see it is very difficult actually, right, to find out the damping ratio for many number of modes. So we generally consider, let's say, the fourth mode and fifth mode, modal damping ratio is the same.
Oh, okay.
But this is nothing to do with this figure. This is just for sake of showing that this might be omega 2, this might be omega 4. So we'll use those things and use the expression obtained from this if my modal damping ratio are same for two distinct modes. Okay.
Yes.
Yeah, we usually try to do that in our practical scenario. So we try to see which modes, two modes are the equal damping ratio and then do it so that our calculations become much easier.